Hello everyone, welcome to Introduction to Machine Learning, Learning Activity 7, our last async activity before we hit our final learning activity, which is the synchronous session later this Thursday. But for this work, we're actually in our lecture. This is the first we're going to see, now that you've gone through a crash course in Python. There's a little bit more Python, but it's more from a database integration perspective. We've given you the basics of kind of the critical path, as it were, of Python, necessary Python things we've got to cover to get you up to speed on, again, the critical path to getting you to this point, which is integrating with our database and then doing data dispersions and visualization. So we're actually going to be getting into some preparatory data science activity. And I'm excited. This is where we're kind of finally getting into, I would say, putting everything together. We did a lot of work on SQL. We've done a crash course on Python. We're still going to be working with Python, of course, but now we're going to be at this point doing some database integration, working with SQL and Python together. So we're going to do some Python program preparation in our lecture. We'll do database integration, talk about what that looks like. We'll talk about dispersive patterns of data, correlation versus covariance, and then core plots. And then on the lab agenda, we've got some pip installs we've got to do. And then we'll get into database integration. We'll do what's called ETL. We'll do some authentication along with that ETL work. It's basic ETL work. It's not like we're using an ETL package, but we have to do some authentication with the database so that Python can pull the data across using PyODBC, and then we'll actually do some labs on doing some statistics and data science, actually getting into some of it beyond just descriptive statistics. So we're actually going to be getting into some nice data science pieces here. So okay. Let's do this. Python programming preparation. So we've got two libraries that we are going to work with new that we have to install. So one is PyODBC. This is a database API that allows us to an application programming interface that allows us to take Python and integrate Python with our SQL Server engine. And then we also have Seaborn. This is a data visualization library, and it's very useful. I would say between Matplot and Seaborn, these are kind of your go-to workhorses when it comes to advanced visualizations within Python. So we're gonna work with Seaborn as well. Okay, so let's kind of step back for a second. This is kind of our rough architecture at this point in time. So a long time ago, in a galaxy far, far away, we had Microsoft SQL Server and AdventureWorks database. We haven't touched that up to this point, but we are going to revisit that now. We've got an API that we're going to establish using PyODBC. We're going to use the ODBC data connectivity framework to give us a hole. It's going to poke a hole into SQL Server that allows us to run SQL. But then we can actually take SQL and very easily integrate SQL into our Python without having to do a lot of. It's actually a very robust framework. There's a lot of cool things we can do with it. So anyway, Python, and then we're going to be using pandas, and then Seaborn for data visualizations. We'll be using pandas to do data dispersion, correlation, covariance. We'll use Seaborn to do data visualizations on that. That's all going to happen. Things like we had mentioned earlier, things kind of ramp up pretty quickly from here. So we've got that on deck for this learning activity. So when we talk about dispersive patterns of data, we're talking about still descriptive stats, but we're actually taking it to another level. We're getting samples, means, standard deviations, quartile ranges. But we're able to do this now, and across multiple. Like what we did before was just looking at one output or maybe a couple columns. We weren't really looking at what central tendencies of data look like as it relates to real data. Quite honestly, now we're actually going to get into the meat of what this looks like for real data. After we get through, just kind of get through what data dispersions looks like, we're going to be talking about the difference between correlation versus covariance. We'll primarily be using the core function or the core method. That's one that we're going to be using within the pandas data framework. Covariance is also another method that we can leverage, and there's differences between covariance. Covariance is an indicator of the extent to which two random variables are dependent on each other. Correlation is an indicator of how strongly these two variables are related. So there's some other things that are a little more difficult to kind of explain in just simple text, but one of the big things that we say in the data science and the machine learning world is that the correlations are what are called standardized values. Covariance are unstandardized values. And when you look at the values here, they can go from infinity negative to infinity positive, whereas correlation can go only from -1 to +1. So negative 1.0 to positive 1.0. The reason that we talk about covariance versus correlation is covariance can give you a lot of wild swings. So, for example, if you're comparing home values, which can be anywhere from 300,000, 200,000, 400,000, it could be as low as really low. Of course, as low as of reasonably, let's say. I know there's outliers, of course, but reasonably, we're talking about home values that usually go from 50 to a million, right? There's a huge swing in home values versus if you try to find the covariance between let's say a person's age. A person's age is reasonably expected to be between 0 and 120, right? But we know that people are living longer, so it's possible that that can go up higher in the future. But for the most part, we know that reasonably humans live to at the top end to be 0 to 100 and let's say 30, just to be safe for today. But maybe 50 years from now, it'll be 140, 150, right? That's not out of the realm of possibility. Where I'm going is, even if we go to the extreme and say 150, the covariant swing in the numbers is not going to be nearly as much as what you might see in home values versus human lifespan. That's why what we use is correlation a lot, because it standardizes the values for us. So regardless of that, right, we would get large swings in the data when we have more voluminous data or larger data values. So covariance can be tougher to kind of interpret. That's why we use correlation for the most part, because it helps to standardize across all, regardless of those swings in values. It standardizes that, so it makes it easier to read. But again, this is one of those things that's a little easier to see. So let's show you what it looks like. Here's a core plot. This is one that shows you core plots from a visualization perspective. This is a Seaborn core plot. We're going to create some core plots in this learning activity. In this case, it helps us to see the correlations between. In this case, you can see some examples here, like miles per gallon to cylinders. So the miles per gallon is negatively correlated to the number of cylinders, which shows that it's a negative 0.85 up here. Right here, miles per gallon shows a negative 0.85 to the number of cylinders. That's how you interpret core plots. There is a positive correlation to the number of cylinders in horsepower. So that's 0.83. Number of cylinders increases weight, which means that as cylinders increase, so does the weight, right? The weight of the car, the weight of the engine. That there's a correlation there. And that's a simple way you can kind of see what this all looks like here. This is, of course, based on engine and mechanical relationships between an engine and certain outputs as it relates to performance. So core plots usually incorporate a color map or a heat map. In this case, black is representing negative correlations, and orange-ish, reddish is kind of indicating of, I think we're going up into that this range here, you can see the gradient. Black is negative 0.8, and then up to like a peachish color of positive 0.8. That is pretty typical. We'll create some gradients of different, just so you can see the different styles. You can create these heat maps using different visualization color schemes. But that's the standard one. We'll create some as well. Just so you understand visually, if you were to do regressions on each of these individually, each variable like x by y, this is an example of how you interpret the individual numbers in the core plots. Remember, a core plot allows you to analyze 20, 30, even 40. It starts to get a little harder to interpret, but a little busy. But you can interpret um, multiple variables all at once versus doing it like a regression, right? But you want to do a core plot, especially to find if there's areas that you should, it's part of the data evaluation process. So that helps you to identify areas to target first, instead of kind of doing it at random, right? Scatter, kind of a scatter plot, approach, rather scatter plot approach, rather just a shotgun scatter approach. That's probably just a better way to put that, where you just kind of picking and choosing variables at random to see which ones have correlations, whether it be negative or positive. Okay, so the things that we're looking for, that we're interested in core plots, are negative correlations and positive. They're both good for us. Negative doesn't mean it's bad. It just means that it has an inverse relationship. So in this case, increase in student absences has a decrease in student grades. That would be a negative correlation. And typically the value that we're looking for is anything above negative 0.5. And if we're really being honest with ourselves, we really want to see negative 6.0 and above. In other words, negative 6.0 to negative 1.0. But negative 0.5, it just depends on the situation. That's when you're getting into territory where there is some correlative capability or correlation between the two. If you show a neutral or zero, so coffee consumption as it relates to shoe size, that's pretty much that's going to be random. So in this case, if we were to do a scatter plot of these two, you would have something that shows, as things approach zero, whether they be like negative 0.25 or 0.25 or negative 0.1 or 0.1 or something like that. As they get closer to zero, that means that you're statistically insignificant. There's no correlation, in other words, between these two, and that's not worth your time in analyzing it in any way, shape, or form. Whereas on the positive core plot, if you have values that are 0.5 and above, that means that you have a positive relationship. So increase in student attendance has a increase in grade. It's proportional. So as one increases, the other increases. So we say that's proportional. And in this case, the negative, if you have a line that looks like that, that's almost a perfect negative. And if you have a line that looks like the one on the right, that's almost a perfect positive. That would be something that shows up like at a 0.9 or higher. You're going to see a line that looks really nice and straight. If you were to do a regression on those variables. So here's another thing to keep in mind too. The core plot doesn't guarantee that the regression is going to be perfect if you do it. It doesn't mean that it's going to come out this way. There's more things that we have to evaluate. And on top of that, that doesn't mean that if you do other predictive analysis on these type of things, that doesn't guarantee that you're going to get a positive outcome. The core plot just says that there is some explainable variance there, or a correlative of variance between two variables. And whether it be negative or positive, that is worth investigating at another level. So this is all still exploratory. Okay, that's enough for, this is one of our longer lectures, but we definitely have a lot more to cover because we're getting into the preparatory data science work as well as the data integration. With that, I'm done on the lecture. Let's go jump over to the lab and wrap this up.